All right, so the last theorem we're going to be talking about in this section is the characteristics of countable sets. So the part one of the theorem basically states that is the union of finite countable sets, finite number of countable sets, still countable? And it turns out it is true. If we have finite number of countable sets, then their union is countable. And the second part of the theorem states that what about the infinite union of countable sets? Well, it turns out that is also countable. So we'll dive right into the proof. So for first part of the proof, we will use induction to show that show that union of finite numbers of countable sets is countable, i.e. the union of I equals 1 through m, ai is countable. All right, how do we do this? Well, just like any other induction proof, we're going to start with the base case. Let A1 and A2 be countable. Then we can list off the elements like this. A1 and union A2 can be listed off like this. A11, A21, A21, A22, A3, A11, A21, A12, A22, A13, A23, and so on. So hence A1 union A2 is countable. We can simply just list off the elements of the both sets consecutively one by one. So we know that the union of A1 and A2 is countable. What about in general? So our inductive hypothesis is that assume A1, A2 up to AM is countable. We want to show that A1, A2, AM plus 1 is also countable. All right, how do we do this? The trick is to let B be A1, A2, and all the way up to AM. Then B, all right, I'll just make this clear. This whole thing is going to be equal to B union AM plus 1. Well, we know that B is countable by our inductive hypothesis, and we know that AM plus 1 is also a countable set. Then by our base case, since these are just two countable sets, A1 intersect A2 intersect all the way up to AM plus 1 is countable. Thus, by mathematical induction, A1, A2, AM is countable. So basically, if we have finite number of countable sets, their union is always going to be countable. All right, what about the second part of the proof? Does this extend does this characteristics of countable set extend in the infinite settings? So if we have infinite amount of countable sets, is the union of their infinite countable sets, infinite number of countable sets still countable? Oh God, sorry. It turns out it is true, but we can't use induction to prove this because it is not finite. But what we can do is use the diagonals. So we're going to use a very clever trick to prove this. So let's say A1 is A11, A12, A13, A15. Let's say we have A2. That goes like A21, A22, A23, A24. And this may take a little while. A5, and so on and so on. So this A31, A32, A33, A34, A35, A41, A42, A44, A45, and our last, well, obviously it goes on to infinity, but for the time's sake, we'll stop here. All right, so how do we list all of these elements in a list? So we want to show that this is countable, and we want to be able to list all the elements in the list. Well, we can't just list A1 all first and then list A2, because it's going to be, A1 is going to extend forever and ever. We're never going to be stopped. We're never going to be able to stop and actually start on A2. So we can't just list all the elements of A1, then list all the elements of A2. Well, what we can do is we can use the diagonals. So we're going to be going like this. We're going to be listing A11 and then A21 and then A12, A31, A22, A13, so on and so on. And why this works is that we know that each diagonal is going to have only finite number of elements. So our first diagonal has 1 element, second diagonal has 2, third diagonal has 3, 4, 5, and so on and so on. So we have finite amount of elements we can list at once. So if we go onto diagonals, we're going to eventually hit all of the elements in this infinite number of countable sets. So that's the proof. We can list off the elements of the diagonals to create a one-to-one correspondence with the natural numbers. Hence, the union of infinite number of countable sets is countable, which finishes the proof. All right, so that's the last theorem that we're going to talk about, cardinality.